Hi students! Today we're going to be solving exponential and logarithmic equations. We'll begin with an exponential equation. An exponential equation is an equation containing one or more expressions that have a variable as an exponent. So if the variable is in the exponent's position, that's what makes an exponential equation such. For example, I've got 27 raised to the 2x plus 5 equals 3 to the negative x plus 7. This one we can use a certain technique on because both 27 and 3 are powers of 3. Using that technique, I can rewrite each of those numbers so that they're equivalent. For example, 27 is 3 cubed, 3 just remains 3. Once I have the bases equal, I can set the exponents equal to each other. If I've got 3 cubed raised to the 2x plus 5, I'm going to distribute, raising a power to a power. Therefore, I have 3 to the 6x plus 15 equals 3 to the negative x plus 7. And again, once those bases are equivalent to each other, our exponents must also be equivalent. Therefore, 6x plus 15 equals negative x plus 7, and x equals negative 8 over 7. We can utilize that technique anytime we can make the bases the same number. Taking a look at that technique a little more in depth, let's see if we can solve a couple examples. We've got 9 raised to the 9 raised to the 8 minus x equals 27 raised to the x minus 3. Those are both powers of 3. So I've got 3 squared raised to the 8 minus x equals 3 cubed raised to the x minus 3. Whenever you have a power to a power, you multiply, so I distribute there. I've got 3 raised to the 16 minus 2x equals 3 raised to the 3x minus 9. Now that our bases are the same, we set our exponents equal to each other. 16 minus 2x equals 3x minus 9. Therefore, 5x equals 25, and x is therefore 5. If you plug x back into your equation, it'll come out to be a true equation. Let's try that one more time, and then I'll give you the opportunity to practice these two on your own. I've got 5 raised to the 2x equals 1 over 125 x to the 10th. 5 and 1 over 125, those are both powers of 5. Therefore, 5 raised to the 2x equals 5 to the negative third raised to the x plus 10. Therefore, I have 5 to the 2x equals 5 raised to the, distribute through, negative 3x minus 30. Therefore, 2x equals negative 3x minus 30. 5x equals negative 30, and x is therefore negative 6. Again, plugging it in, it will make it a true equation. Go ahead, take a moment, and solve these next two on your own. All right. Hopefully you were able to solve these next two successfully. The answer for this one was x equals 2, and the answer for the last one was x equals negative 3. And those were the next two. Let's continue on. Now on this next example, if you look, I've got 4 raised to the x minus 1 equals 5. I can't make those the same base. 4 and 5, those aren't, you can't convert those to the same base. They're not both powers of 2, they're not both powers of 3. You can't convert them to the same base. So when you have a situation like this where you cannot change them to the same base, this is when we have to apply a logarithm to both sides. Now, if you look at this example, I've got it worked out for you here. 4 raised to the x minus 1 equals 5. Therefore, I'm going to take the log of both sides. We've talked about it a few times now that logarithms and exponents are inverses of each other. So if I want to solve for an exponent, which I do, I'm going to apply a logarithm to both sides. Logarithm base, you can choose any base, but in this case, I want base 4. because watch what happens. When I take log base 4 of 4 to the x minus 1, this was the inverse property. Log base 4 of 4 is 1. The x minus 1 comes out front. That's power property. Therefore, I have x minus 1 multiplied by log base 4 of 4, which is 1. In essence, these cancel out, making 1, and the x minus 1 comes out front as the coefficient. Therefore, that's why I chose log base 4. If this were a 7 right there, I would have chosen log base 7. So now I've got log base 4 of 4 to the x minus 1. That converts to x minus 1 multiplied by log base 4 of 4. Again, that cancels out to 1. And then I've got log base 4 of 5 on the right-hand side. Whatever log base you apply to the left-hand side, you also apply that log base to the right-hand side. We also discussed this the other day. I said you need to use the change of base formula anytime you're using my calculator. The reason for that is, again, I disabled log base on the calculator. Therefore, my calculator only does base 10. So I've got to do log base 10 of 5, the argument, divided by log base 10 of 4, the base. That's how I'll convert that to a decimal. So log of 5 divided by log of 4, that comes out to be 1.16. And then, of course, I add the 1, and I get 2.16. And that's my final answer. Looking at this technique, again, you'll need a graphing calculator whenever you can't change the base so that they're equivalent to each other. So you'll need a graphing calculator anytime you can't get a common base there. Let's practice a couple of those. I've got 2 raised to the 3x equals 15. Again, the 2 and the 15, they don't have any in common. You can't change them both to 2s. You can't change them both to 3s, 4s. They have nothing in common. Therefore, I'll take the log of both sides. We will take the log base 2 of both sides. Log base 2 of 2 to the 3x equals log base 2 of 15. Again, using the power property, that comes out front. So you've got 3x multiplied by log base 2 of 2 equals log base 2 of 15. Log base 2 of 2, that's 1. So I've got 3x equals, let's use the change of base formula over here. Again, I need my graphing calculator. Let's use base 10. 3x equals log base 10 of 15 divided by log base 10 of 2. Let's type that in. Log of 15 divided by log of 2, 3.906 divided by 3. Therefore, x equals 1.302. Again, AP Standard students are 3 decimal places, so anytime it doesn't tell you how many to round to, always round to 3. That will apply to this log test as well. All right, so let's go ahead and look at the next one. Same concept. However, we always get the base with the exponent isolated first. Then we apply a log to both sides. So for each one of these next few, you're going to add the 6 both sides and then take the log. We'll divide by 3 on both sides and then take the log. We'll subtract 8 on both sides and then we'll divide by 7 on both sides. We'll subtract 4 on both sides and divide by a negative. You always get the base with the exponent isolated before applying a logarithm. So again, going back up to the top here, we'll add the 6 to both sides. I get 15 raised to the x plus 8 equals 18. Therefore, what base should I choose? Base 15. Log base 15 of 15 to the x plus 8 equals log base 15 of 18. That becomes x plus 8. Let's use change of base and solve. Let's go to the calculator. Log of 18 divided by log of 15 minus 8. Negative 6.933 is our final answer. Negative 6.933. Take a minute, pause the video, and try solving these. Try solving the third and the last. And then we'll go over this middle one together. The third example on this page comes out to be x equals negative 0.102. The last one on this page turns out to be x equals 6.931. Let's take a look at the one in the middle. I skipped him for a reason. The one in the middle, I still need to isolate my base first before applying a log. So I subtract 8 first. 7e to the 2x equals 13. Now divide by 7. E raised to the 2x equals 13 over 7. Now, I need to choose an appropriate base. Well, what type of log is base e? The natural log, yes. So I'll apply natural log to both sides. Log base e is natural log. Therefore, natural log of e to the 2x equals natural log of 13 over 7. Again, log base e of e, that's 1. So I'm left with 2x equals natural log of 13 over 7. We could do that in our calculators. Natural log of 13 over 7 is 0.619. We'll divide by 2, and we get 0.310. And that was the answer for the fourth question right there. This is the technique that you'll use to solve when you cannot change the base to the same value. This would be on the calculator portion of the log test. Let's continue. All right, solving for the indicated variable, solve for t. Again, logarithms are used anytime you're solving for an exponent. So let's see if we can isolate t. First thing, I need to get the base by itself, so I'll divide by k. Y equals, y over k equals b to the at. Then I'll apply a log to both sides. What base? B. So log base b of quantity y over k equals log base b of b to the at. Again, those cancel out. Therefore, log base b of y over k equals a times t. Dividing by a will isolate t. Therefore, t equals log base b of quantity y over k all over a. Try to solve the second equation for x. I'll give you a minute. Pause the video. When you solve the second equation for x, you'll find that x comes out to be log base k of quantity -4 over h minus 1 plus 5. That's as simplified as we can get with that one. Let's continue. What we just finished looking at were all exponential equations. The variable was in the exponent. These are all called logarithmic equations. A logarithmic equation is an equation with a logarithmic expression that contains a variable. You can solve logarithmic equations by using the properties of logarithms. So using all the properties of logarithms, let's review. We've got product property, we've got quotient property, we've got power property, we have inverse property, and we have the change of base formula. So you can use any of those properties that we discussed last block to solve these equations. Remember, power property comes first. You always apply the power property first to solve in most instances. All right, so let's take a look at this one. I've got log base 10 of x plus 2 multiplied by log base 10 of 2 equals 2. Again, I typically do power property first. In very rare instances, I may not do power property, but most of the time I do. So here we go. I move the 2 up. That becomes the exponent log of x plus log of 2 squared. Well, that's log of 4. So then I use the product property. That addition sign tells me I can multiply. Therefore, log base 10 of 4x, quantity 4x, equals 2. At this point, I've also showed you this. I log roll. Again, here's my log roll. Start at the base. You always roll towards the equal to sign, around, and stop at the argument. So 10 raised to the second equals 4x. Therefore, 10 squared equals 4x. 10 squared is 100. 100 equals 4x, and x equals 25. First thing I did, I used power property. Second thing I did, I used product property. Third thing, I log rolled. And lastly, I solved for x. And that's how I would solve a logarithmic equation. Let's try some examples. Okay, so let's start with something basic. I've got log base 12 of x plus log base 12 of x plus 1 equals 1. That plus sign, what property is that? The product property. Therefore, I can change this to log base 12 of x times x plus 1 equals 1, which is equivalent to log base 12 of x squared plus x equals 1. Once I have a single log, I'm going to log roll, and I get x squared plus x equals 12. 12 to the first equals x squared plus x. 12 to the first. Therefore, let's solve for x. I've got x squared plus x minus 12 equals 0. Therefore, x plus 4, x minus 3 equals 0. X comes out to be negative 4 and 3. However, look at the directions on this slide. It says solve and check. Solve and check. On some of these equations, we will also produce extraneous solutions. Therefore, take your answers and plug it back in. Let's see what happens. When I take negative 4 and plug it back in, I get log base 12 of negative 4. That's a problem. Remember, we talked about the definition of a log. The base can't be negative and the argument can't be negative. Therefore, x equals negative 4. That is extraneous. The only solution that works is 3. All right, let's try another one. I've got log base 10 of 8 plus log base 10 of x multiplied by 3 equals 3. What do I do first? Power property, that's right. Let's move the power up there. I've got 3 equals log of 8 plus log of x cubed. Therefore, I can use product property next. I've got log of 8x cubed equals 3. What's the base right there? That's base 10, that's right. We roll it. 10 cubed equals 8x cubed. We cube root both sides. 2x equals 10. Therefore, x equals 5. Taking the solution, plugging it back in, it works. I don't have any extraneous solutions because that's positive. It's positive, no problems. Let's take a look at, let's work on the third one here. This one looks a little interesting. So I've got natural log of x plus 25 equals 2 plus natural log of x. All right, first thing I'll do is I'll move the logarithms to one side. So I've got natural log of x plus 25 minus natural log of x equals 2. What does the negative sign tell us? What property is that? Quotient property, yes. So I've got natural log of x plus 25 divided by x equals 2. What is the base right there with a natural log? That's base e, right? So I'm going to roll an e. I would need a calculator for this question. I will not expect you to roll an e without a calculator. You've got e squared equals x plus 25 over x. Let's see. Let's grab this calculator. I've got e squared. So 7.389x equals x plus 25. Let's subtract 1 minus 1. 25 divided by my answer comes out to be approximately 3.913. Again, round to 3 decimal places. That's AP standard. All right, well, I've solved 3 of them out for you. Go ahead, pause the video, see if you can solve the next 2. The second to last solution comes out to be 2, and the last one comes out to be 4. All right, let's continue. Now, we have to use change of base formula if the bases aren't the same, right? So I look at the bases, I've got 2 and 4. I can't use product property because my bases aren't the same. But watch what I can do. Let's manipulate this and change it to base 2. I've got log base 2 of 2x over log base 2 of 4. Right? So I've got log base 2 of 2x over 2. Well, I showed you this little trick in class. Dividing by 2 is the same as multiplying by a half. That's right. So I've got log, 1/2 log base 2 of 2x. That's the same as 1/2, That's the same as log base 2 of the square root of 2x. All right, so let's see what I have. I've got this now converts to this, right? Well, now I can use product property. So I've got log base 2 of x multiplied by root 2x. Let's write that down. Log base 2 of x plus log base 2 of root 2x equals 2. Now I can apply the product property because my bases are the same. I've got log base 2 of x multiplied by root 2x equals 2. Well, this looks really messy, but it's going to turn out okay. Let's see what happens. I need to log roll. I've got x multiplied by root 2x equals 4 because 2 to the second equals 4. How am I going to solve this? Yeah, that's right. You square both sides. So let's square both sides. I get x squared multiplied by 2x equals 4. So therefore I have 2x cubed equals 4. Hi, I'm filming a video right now. Could you come back in a few minutes? Okay. Therefore, x cubed equals 2, and x equals cube root of 2. All right, let's look at another one. I've got log base 25 of 400 minus 2 times log base 5 of x plus 1 equals 1. I'm going to change these both to base 5. So I've got log base 5 of 400 over log base 5 of 25 minus 2 log 5 x plus 1 equals 1. All right, so let's see what happens. I've got log base 5 of 400 over 2 minus log base 5 of x plus 1 quantity squared equals 1. So again, using that same little trick, I'm going to simplify this a little bit further, and I get log base 5 of 20 minus log base 5 of x plus 1 quantity squared equals 1. Let's continue. Now I can use the quotient property. So I'm going to go ahead and solve this one out. I've got log base 5 of 20 over x plus 1 quantity squared equals 1. Let's log roll. Whoop. So 5 equals 20 over x plus 1 quantity squared. Therefore, 5 quantity x plus 1 squared equals 20. I've got x plus 1 quantity squared equals 4. Square root. X plus 1 equals plus and minus 2. Therefore, x equals negative 3 and 1. But again, take a look. If I plug in negative 3 to x right there, that comes out to be a negative, which is a big problem. Therefore, x is not negative 3, x is only positive 1. So whenever possible, use the change of base formula. You can choose any base, but if you want to make your bases match, you definitely want to take that into consideration. All right, let's continue. Now, the last topic of the day, use substitution. Use substitution is a technique that's also used in calculus. So when you're calculating integrals or derivatives, you'll sometimes see use substitution used as well. Let's take a look at how use substitution is useful. We've got x to the 4th minus 16x squared plus 60 equals 0. Therefore, I can simplify this and change it into something a little bit less complicated or less intimidating. Defining what u is half the battle. So if we look at this equation, we want to set u equal to x squared. Watch what happens if we do that. If u is equivalent to x squared, we can plug in x squared right there. We can plug in u into the first term. That would just be u squared because x squared is x to the 4th. That would be minus 16u plus 60 equals 0. The whole idea behind u substitution is that it simplifies the equation. Now, instead of being a quartic, we have a quadratic. We've got a quadratic, we can factor it, and we solve for u. Now, here's the thing. Since we have a solution for u, we still need to go back and set it equal or solve for x. Therefore, we take our u substitution, whatever we set equal to u, and we now set that equal to my solution. So if u was defined as x squared up at the top and u is 10, taking those two pieces, we can say x squared equals 10, x squared equals 6, and now we've got x equals plus and minus 10 and x equals plus and minus 6. The process of u substitution is a simple way to reduce or simplify an equation. It's not that helpful in this instance, but you'll see on the next two, it makes it a lot A lot less intimidating. So let's take a look at a couple more examples. All right, last two. I've got log base 3 of x quantity squared plus log base 3 of x squared. Now, these are different. This, the entire log is being squared. This, only the argument is being squared. So I'm going to define u as log base 3 of x. Watch my rationale. So I've got u is log base 3 of x. Therefore, this first term is u quantity squared. This exponent becomes the coefficient using the power property. So now that's 2 multiplied by log base 3 of x, or 2u, equals 3. I've got u squared plus 2u equals, subtract 3 equals 0. Let's simplify. U plus 3, u minus 1 equals 0. Therefore, u equals negative 3 and 1. Keep in mind, we just solved for u. We did not solve for x. Let's plug it back in. If u is defined as log base 3 of x, I take the negative 3, plug it in. Negative 3 equals log base 3 of x. How do we solve that? We log roll. Whoop. 3 raised to the negative third equals x. Therefore, x equals 1 over 27. That's one of our answers. Let's substitute in again. Since u is also 1, 1 equals log base 3 of x. And therefore, 3 to the 1 equals x. Log rolling. Therefore, x equals 3. So I have two solutions for x. X equals 1 over 27 and 3. U substitution. Let's do one more using U substitution. I've got log of the cube root of x equals the square root of log x. What do you think I should define u as? Log x. Let's try. U equals log x. All right, so let's see if we can simplify this. This right here is the exponent, right? Cube root. How could I write that as an exponent? That's right. That's raised to the 1/3 power. So this is actually log of x raised to the 1/3 power equals log of x raised to the 1/2 power. All right, so I move the 1/3 out front. I've got 1/3 log x equals log, no, I'll keep it like that. Log x to the 1/2. Now, this still doesn't look very pretty, but let's work with it. If u equals log x, I've got 1/3 u equals u to the 1/2. Now, I changed the square root to a 1/2, but in retrospect, I don't think it makes it look any better. Let's change this back to a square root. 1/3 u equals square root of u. How do I solve this equation? I square both sides, sure. I get 1/9 u squared equals u. Therefore, 1/9 u squared minus u equals 0. I can factor out a u. 1/9, u multiplied by 1/9 u minus 1 equals 0. Let's see what u equals. U equals 0, and what? U equals 9. All right, so if those are answers for u, again, keep in mind we're not solving for u, we're solving for x. Let's take those, plug them back in over here. So I've got 9 equals log x. I also have 0 equals log x. Let's roll both of those. 10 raised to the 9th equals x. That's one of our answers. 10 raised to the 0 equals x. Therefore, x is also 1. I log rolled right here, and I log rolled right here. Those are our two solutions for x. And that is U substitution. Students, that is your lesson on logarithms and exponents in terms of equations, solving equations. If you have questions, please ask the substitute on Thursday when I'm out, or of course tomorrow if I see you in class, you're more than welcome to ask me. Have a great day. Bye-bye.